So before we begin our chapter on volume, we're going to do a little bit of an introduction to three-dimensional figures. So three-dimensional figures include cylinders, cones, spheres, pyramids, prisms, and there are different ways to classify them. Many three-dimensional figures are called polyhedra. That's the plural. Polyhedron is singular. And a polyhedron is a closed three-dimensional figure in which every surface is a polygon. So in this one, every surface is a pentagon. Here, every surface is a triangle. Here we get squares and triangles. But they're three-dimensional figures and they're closed. So something like a cylinder here would not be a polyhedron because a circle is not a polygon. Every surface has to be a polygon. So this is not a polyhedron. A sphere is not a polyhedron. So a polyhedron is a specific type of three-dimensional figure. So back to polyhedra. Here are some, but two of the most common types of polyhedra are prisms and pyramids. So we'll start with prisms. A prism is a polyhedron that has two bases. Those bases have to be congruent and parallel to each other, and every other surface has to be a parallelogram. And it's going to be really, really important for this volume and surface area problems to be able to look at a figure and decide where the bases are. So for example, on this prism, if you're thinking that this is the base, that's not correct, because there have to be two congruent parallel surfaces that are called the bases. So this and this, these two triangles, are congruent parallel surfaces, and the other surfaces are parallelograms. So this rectangle is a parallelogram, and this surface is a parallelogram, and that back surface is a parallelogram. So here's another prism. Can you spot the bases? Two congruent parallel surfaces that are connected by parallelograms. So it's going to be this front pentagon and this back pentagon. Those are the congruent parallel surfaces, and all the other surfaces that connect them are parallelograms. Now here we have choices about what we want the bases to be. We could say the bases are the front rectangle 10 by 4 and the back rectangle 10 by 4. And those are connected by 4 other parallelograms. But we could also say that this left surface and this right surface are congruent parallel surfaces, and they're connected by parallelograms going across. We could also say the front, which one did I not do yet? The bottom and top. So we could say that this is one of the bases, and this is another base. Those are congruent parallel surfaces. And the other 4 surfaces around are all parallelograms. So those are prisms. Pyramids are another type of polyhedron. A pyramid is a polyhedron that only has one base, and all of the other surfaces are triangles. So here the base is a hexagon, so this is a hexagonal pyramid. Here the base is a rectangle, so this is a rectangular pyramid. Here the base is a triangle, so it's a triangular pyramid. So really try to get the difference clear in your mind about prisms and pyramids. Now there's something called Euler's formula. And it has to do with a pattern about on any kind of polyhedron. So this applies to these, it applies to these and these. Anything on this page, there's a pattern about the number of faces and bases and edges and vertices. So faces are the flat surfaces, the polygons. So I'm going to start with, I'll start with this one. This one has 6 faces, 6 flat surfaces, top, bottom, left, right, front, back. The vertices are the corners. They're where all the segments intersect. So for example, these 3 segments intersect at this vertex, that corner. Here's another vertex, here's another vertex. This has a total of 8 corners, 1, 2, 3, 4, 5, 6, 7, 8 vertices. And edges are the segments. Edges are where the faces intersect. So for instance, this top surface, this top face, and this face intersect along that edge. So that's one of the edges. So altogether, if you count up the edges in this prism, you should see 12. There are 4 segments here, there are 4 segments here, and there are 4 more going across, total of 12. All right, let's try this one down here. So this one, how many faces do you see? How many surfaces? There are 4. 1 triangle on the bottom, 3 triangles going around. How many vertices do you see? There are 4. 1, 2, 3, 4. How many edges do you see? How many segments do you have to draw to make that picture? And I see 6. 3 segments down here to draw the bottom triangle, and 3 more segments that come down from that top vertex. Let's look at one more. Let's look at this pentagonal prism. So, can you pause the video and see if you can count up the faces, vertices, and edges? And hopefully you saw, let's see, 7 faces. Now, I should say, of the 7 faces, 2 of them are bases, the 2 that are colored in red, and the other 5 are called lateral faces. So the parallelograms that connect the bases are the lateral faces. So over here, the 2 red bases, plus the 4 other rectangles, those are the lateral faces. So 6 faces altogether, 2 bases, 4 lateral faces. The pyramid, where we said has 1 base and 3 more triangles, if this is the base, that's one of the 4 faces. The other 3 faces are called the lateral faces. So lateral faces means the faces that are not the bases. Anyways, let's see how you did. 7 surfaces. There are 10 vertices. 5 on the front, 5 on the back, 5 corners here, 5 corners here. And the edges, if you count all the segments to make this picture, well, there are 5 here, there are 5 here, and there are 5 going from front to back. Total of 15. So can you spot a pattern between these 3 numbers, a way to connect a relationship between these 3 numbers that is also true for these 3 numbers, and it's also true for these 3 numbers? And the pattern is, on any polyhedron, the number of faces plus the number of vertices is always equal to the number of edges plus 2. 6 plus 8 is 14, that's equal to 12 plus 2, 14. 4 plus 4 is 8, it's equal to 6 plus 2 is 8. 17 is equal to 15 plus 2. So that's just called Euler's formula. Faces plus vertices equals edges plus 2 for any kind of polyhedron. A few more things. And by the way, these notes, I created these 2 documents this morning. If I remember, I'll try to link a PDF of them to the video in case you want to have a printout or a hard copy or a digital copy. So one more thing about polyhedra. There are 5 regular polyhedra. A regular polyhedron, also known as a platonic solid, because they were studied extensively by Plato. So it's a special kind of polyhedron. It's a polyhedron where every surface is the same regular polygon. So for instance, a cube is a regular polyhedron. The general term for a 6-sided polyhedron is a hexahedron, but if every surface of that 6-sided polyhedron is the same regular polygon, in this case every surface is the same square, it's called a regular polyhedron. What also has to be true is that every corner you have the same number of surfaces coming together. So at every corner of a cube you have 1, 2, 3 faces intersecting. So here's a regular tetrahedron. A tetrahedron is a 4-sided polyhedron. what makes this regular is that every surface is a regular triangle. An equilateral equiangular triangle here, an equilateral equiangular triangle here, one in the back, one on the bottom. If you were to unfold it, you would see these 4 congruent equilateral triangles. So only 5 regular polyhedra exist. There is a regular octahedron. It is possible to take 8 regular triangles, equilateral, equiangular, and fold them up to form this shape. The most surprising one is a regular dodecahedron. If you take 12 congruent regular pentagons, you can tape them together and close up a region of space, and it's called a regular dodecahedron. And the only other one that you could make using just one repeating regular polygon is that you could actually take 20 equilateral triangles and fold them up, and they'll perfectly close up a region of space to form a regular icosahedron. So again, these are the only 5 that exist. And finally, words I'm sure you're familiar with: cylinder, cone, sphere. They're not polyhedra, but they are 3-dimensional figures. Cylinders have 2 bases. Cones have 1 base. Spheres don't have any bases, and these don't have any faces. The word faces is really just reserved for a polyhedron. So something that's beyond the scope of our course, but I'm just going to mention to you. In all of our cylinders and cones, the bases are going to be circles, but technically they don't have to be. So even something with a weird shaped base like this, I'm not even sure if I really know how to draw what I'm trying to draw here, but you might get the idea. Any shaped base where every point on it is connected to one point above it forms a cone. So this is actually a cone, even though the base is not a circle. Similarly, let me see if I can do a little better on this one. This is a cylinder. Something like that, if you can sort of picture a smooth 3-dimensional shape where the top and bottom are congruent, smooth surfaces, and they're connected from top to bottom. That's a cylinder, that's a cone, but for our purposes, and generally speaking, when people use those words, the bases are circles. So that's a whole bunch of vocabulary I wanted to introduce you to before we start the circle chapter. Before we start the volume chapter. Okay, have fun.